line tangent to y equals x squared plus 2x plus 4 that passes through the origin. So what I want to point out first is that this graph does not pass through the origin. What they're saying is that we have the equation of a line tangent, and that equation passes through the origin. So what I mean by that is x squared plus 2x plus 4, it's not actually passing through the origin. X squared plus 2x plus 4 looks more like something like that. It doesn't pass through the origin, but we want to find like, okay, well, you have a tangent line that does pass through the origin. So it might look something like this. So we want to know what's the equation of that tangent line. So there's a couple things we know about the tangent line. We know the tangent line passes through the origin. We know it's going to pass through some point on this function. And we know the slope of the tangent will equal the slope of the function at that point. So let's say it passes through this point, we'll call it x1, y1, and then it passes through 0, 0. Okay, so if I were to find the slope of the line tangent, it's going to pass through these 2 points. So I know the slope is going to be y1 minus 0 over x1 minus 0. Okay, well, what is y1? That's going to be x of 1 squared plus 2 times x of 1 plus 4, because that is the y coordinate, right? If x is 1, then y would be 1 squared plus 2 plus 4. If x is 2, y would equal 2 squared plus 2 times 2 plus 4. So I'm just using, x sub 1 squared plus 2 times x sub 1 plus 4 to represent the y coordinate at this x sub 1 coordinate. Okay? So that's going to be the slope between those 2 points. But another way to find the slope is by using y prime at x sub 1, right? So if we find y prime at x sub 1, that would be 2 times x sub 1 plus 2. So I just used the power rule to find y prime. So both of these are 2 different ways to find slope, right? Because it's the equation of a line tangent. So it's the slope of the line that passes through these 2 points, 0, 0, and x1, y1, where x1, y1 lies on the original function. And then it's also, because it's a tangent line, the slope equals y prime of x of 1. So what I'm going to do is I found these 2 forms of my slope, and I can set them equal to each other. So 2x sub 1 plus 2 is equal to x sub 1 squared plus 2 times x sub 1 plus 4 over x sub 1. Multiply both sides by x sub 1. I get 2x sub 1 squared. I should have used something different than x sub 1. Plus 2 times x sub 1 is equal to x sub 1 squared. X sub 1 squared plus 2 times x sub 1 plus 4. Subtract everything from both sides, actually. So these will cancel. I get x sub 1 squared minus 4 is equal to 0. So that's x sub 1 equals plus or minus 2. Okay. Which means I kind of have what I have as like x, like what I have drawn up here, where I have a positive x value. But I'm also going to have something like over here where the slope, okay, it's not an exact graph, but it's going to be like maybe like here, where the tangent line passes through the origin and passes through x equals -2 at that function. And so we actually have 2 equations of the line tangent that will work here. So let's solve for my slope at x equals -2. So that would be 2 times -2 plus 2, which is -2. So we're going to have y equals -2 times x plus 2. And then if I plug -2 into the original function, I get 4 minus 4 plus 4, which is 4. Okay, so that's one of my equations of the line tangent. And then the other equation, oh, you know what? I could have just used the fact that it goes through the origin and just done 0, 0. That would have been easier. That's okay. And then my other equation was m is equal to 2 times positive 2 plus 2, which is 6. And then I get y equals 6. Well, it's just going to be 6x. But if I use the same point, x minus 2, plug -2 into my original function, I get 4 minus 4 plus 4, which is Oh, wait, that's not right. Let's try that again. If I plug 2 into my original function, I get 4. Oh, I get 4 plus 4 plus 4, which is 12. Okay, so my 2 equations of the line tangent would be this one and this one. But again, I chose to do this the hard way. I don't know why. It goes through the origin, so you could have just done y equals negative 2x and y equals 6x. Once you find your slope, if it passes through the origin, it's just y equals mx. You don't have to do a y equals mx plus b situation. Okay, so let's go ahead and do 42. Kimberly's velocity is blah, blah, blah. Calculate the average velocity. Okay, so we're given velocity and we're calculating average velocity. We're not calculating the average rate of change of velocity. We're just calculating the average of the thing I was given. If you're calculating the average of the thing you are given, that's going to be 1 over b minus a times the integral from a to b of your function. Okay, so that's going to be my average velocity. And that's for Kimberly. Okay, I'm going to do Varog's, and then I'll do when is each bicycle traveling at their average velocity. And I'll show you that on the calculator. So Varog, his distance, so not his velocity, but his distance is given by this. So if we're calculating his average velocity, velocity is the slope of distance. Velocity is the slope of distance. So find the average slope from 0 to 6. That would be s of 6 minus s of 0 over 6 minus 0. Okay, so in one I have to use the integral formula. In the other one I am using the slope formula. Okay, and then I would just plug that into my calculator, which I will show you here in a second. Okay, so what I am going to do is I am going to calculate my average velocity for Kimberly. So that's going to be 1 divided by 6 times the integral from 0 to 6 of, you know what, I'm going to enter y equals. Y is equal to 2.3 to the x times the sine of x divided by 2. So I entered my function. All right, and then going back to my interval, my integral, I should say, that's going to be dx. All right, so I calculate that. I get 16.102. So 16.102 is Kimberly's average velocity. I want to figure out when her average velocity is equal to her actual velocity. When is she traveling at 16.102 miles per hour? So I'm going to store this as an alpha. I'm going to say alpha A is what I'm going to store it as. Then I am going to graph both the original function and alpha A. And let's see when these two things are equal to each other. Let's see if my window makes sense. Okay, my window does not make sense. Okay, so it's going to be between, let's see, x is in hours, it looks like. So 0 to 10 is probably fine. But her average velocity was 16, right? So we're going to, our y max needs to be like 20. Okay, so that we can actually see where these lines intersect. All right, so we have, it looks like 2 answers, but remember we're only going from 0 to 6. So 1, 2, 3, 4, 5, 6. So this point of intersection, I'm guessing, is on the outside of that point of interval. But let me just double check if that's true. First curve, enter. Second curve, enter. Guess. When you have 2 points of intersection, that guess feature is important because it's going to find the point of intersection that's closest. Yeah, so you can see that point of intersection is outside of my interval, so I'm not going to use it in my answer. Okay, so intersect, first curve, enter. Second curve, enter. Guess. So now I need to get close to my other point of intersection. And it's 3.343. So at 3.343 hours, Kimberly is traveling at her average velocity. 3.34 hours. 343. 3.343. A lot of threes. Okay. So that's Kimberly. And then Varog, we're going to do something similar, but again, his is not hers. I don't know. Their function is not a velocity function. It's a position function. So I am going to find the average slope. All right. Let's clear that out. Okay, so I've got my my original function for distance. And for this, what I'm going to do is, remember, it's S of 6. Enter a second insert parentheses. Okay. S of 6 minus S of 0 divided by 6 minus 0, so that's 6 equals. All right. Now, this is the average velocity. So Varog's average velocity is 19.907 miles per hour. I'm going to store this as an alpha. I'll call it, wrong button. Storing it as alpha A. All right. And we are going to calculate when is the average velocity equal to the actual velocity. Okay, now I don't have a velocity up here. This is the distance. So I'm going to have to come up with a velocity function. So the velocity is going to be the slope of distance. So I'm figuring out here, this is almost more like the mean value theorem. When is the average slope equal to the actual slope? So the derivative of 20t is 20. The derivative of 2 sine t is 2 cosine t. And so that's my velocity function. Velocity function, when is that equal to the average velocity? Let's graph it, see what we have. Okay, window doesn't work here. Let's see, the y max, okay, the average velocity was almost 20. It was 19 point something, so I'm going to make this like 24 so I can make sure I can see what's going on. And remember that we want the times over the interval from 0 to 6. So it looks like we have 2 points of intersection that'll work here. So second calc, intersect, first curve, second curve, guess, get close to it. Okay, so my first point of intersection is 4.666. So at 4.666 hours, Varog is traveling at their average velocity. Their actual velocity is equal to their average. And then let's do this one more time. First curve, second curve, and get close. Press enter. And then also at 1.617 hours, Varog is traveling at their average velocity.